In 8.5, we talk about polar equations for conics, and one big advantage is that polar equations for conics are very easy to rotate. We don't have to do any matrix multiplication. Another pro is that it's the same equation for parabola, ellipse, or hyperbola, just different numbers in the equation, but it's the same exact setup. But one big con, or the price that we have to pay for those two advantages, is that whenever you do a conic, you need to have one in polar. You need to have one focus point at the pole. That's always going to be necessary. So in this particular picture, you have a conic. It could be a parabola. This could be a piece of a parabola. It could be a piece of ellipse. It could be a piece of a hyperbola. Any of those. And in any case, the directrix would be here. The difference would be depending on what the E value is. That would, if we knew that, we would know what kind of conic this is. E, of course, is always the ratio of the distance from the focus to a point over the distance from a point to the directrix. When you look in the textbook, you'll see that in polar equations they use the letter K, and what K stands for is the distance from the focus to the directrix. We've previously learned that if the shape is an ellipse, that distance right there from the center point is d minus c. If it's a hyperbola, so there's the center point over there, that same distance would be c minus d. So in general, for both of those, k would equal the absolute value of d minus c. Of course, for a parabola, that distance right there would be 2p. Distance of 2p, so k would equal 2p. So just to not get all confused with that, they just call that distance k. So we don't have to get involved with p's and d's and c's. Okay, so the eccentricity would be the ratio, the distance, f to p, which in polar would just be r. R is that length, over the p to the directrix, which would be k, subtracting out that little distance right there, which would be r cosine theta, So we would have our ratio. And then we could cross multiply our ratio, and we could move things around and solve for r, and we could get, this is the standard form for a polar equation that would be for either a parabola, ellipse, or a hyperbola, and that would depend on what the E value is. If we knew E, we would know what shape this is for. But notice the pattern here is that when the directrix crosses the positive x-axis, we have a positive cosine in our formula, and we'll see how that pattern changes when the directrix is in another location besides the positive x-axis. In this picture here, I've I've rotated the picture around so that now our directrix is over crossing the negative x-axis, and the conic is going in the other direction. Notice that I say x-axis, even though we're in polar form, it's still conventional to say x and y axis if it makes communication just easier. Again, k is the distance from the focus to the directrix. This time our ratio will be r over this distance right here, which will be k minus this angle. The angle right here would be pi minus theta. Here's theta right here. So it would be r cosine of that angle. R cosine of that angle would be this little part right here. I could expand out the cosine difference formula. And of course, that last part right there will be 0 because sine of pi. Cosine of pi would be -1. So I can simplify, I can cross multiply, I can rearrange, and I can solve. The punchline or end of this thing is that if it crosses, the directrix crosses the negative x-axis, then all we have is a minus here with the cosine. So this is all nice proof, but this is what you need to remember. It's just like the previous one. All right, so now we have the conic, which again is a generic conic, could be parabola, ellipse, or hyperbola, depending on the E value. And the directrix is above it. K, again, is the distance from the focus to the directrix. and the point is located at an angle theta from the x-axis. And our ratio, as before, is our distance r and our distance, which would be k minus this little y value, r sine theta. And again, we could cross multiply, and we could isolate the r, and we could solve for our equation. Notice that when the directrix crosses the positive y-axis, we have positive sign. So probably no surprise to learn that when the directrix is crossing the negative y-axis, the only difference would be that would be a minus. Okay. Now another method that we could do this, and this is just for kind of proof purposes, I could say, well, what if we take the original cosine one, so with the plus, so what if we had the directrix over here and our conic going this way, and we just rotated everything. We rotated that entire picture 90 degrees to make this picture. And so if I put a minus pi over 2, that would mean that I'm going to move something or do something 90 degrees. And you'll notice that when I do a little bit of factoring out the minus sign, remembering that cosine is an even function so that the minus will disappear when pulled out, remembering our cofunction identity, which is pi over 2 minus theta of cosine is the same as sine, that I get the same exact equation. So the point of all this math is not something you have to recreate, but the point is that if you want to rotate a conic in polar form any amount of radians or degrees in the counterclockwise position, you just need to put that right here. Notice that when I want to go a positive 90 degrees, I put minus pi over 2. And that's because we're inside the parentheses, so we do the opposite. If I wanted to rotate a picture clockwise 30 degrees, I put plus 30 right here. Again, it's the opposite because it's in the parentheses. All right, one little last bit of theoretical business before we get to the examples in the second video. So as far as focal width goes, if we locate P at this particular location, then it would be at one end of the focal width. And again, eccentricity would be PF over PD. PD is K. And so we can solve for PF as EK, which means the entire focal width is twice that, which would be 2EK. Sometimes I see it with absolute values around it, but E and K are always positive values. So whether you put the absolute value or not is no problem. One last thing is that this directrix equation, in this particular picture, the directrix equation is x equals minus k. K is always a distance, so it's always positive. X equals minus k. The other places the directrix could be is over here, so x would be k. Up here, so y would be k, or down here. So those are the only possibilities for the directrix equations.